Evaporation as a concept is it's like a variant of heat transfer, a bit different. So we're going to look at it in a little more detail. These are the objectives. So we're looking at the difference between evaporating and boiling, factors affecting evaporation, and consequences and applications. So both boiling and evaporation are vaporization. They both involve turning liquids. I'll probably say water most of the time, but in reality any liquids, into gases. Evaporation only happens on the surface of a liquid. Okay, it happens at all temperatures. It happens at 0 degrees Celsius for water. It happens at all temperatures for water. And the speed with which it happens, the rate of evaporation in kilograms per unit time or whatever, is dependent on a variety of factors that we'll look at in a minute. Boiling, on the other hand, is a quite different process. Boiling happens when a certain amount of the liquid has enough energy to just separate. In the case of a pan boiling, that will happen at the bottom of the surface of a pan because that's going to be the hottest place. When that turns into a gas, it forms a bubble. That bubble is filled with the gaseous form of the liquid, so in this case water vapor. It's not gas, it's not air, it's bubbles of water vapor, which then rise, obviously, because they're much less dense. It happens at a certain temperature. That temperature we call the boiling point, and that boiling point is dependent on other factors, mostly on the air pressure, how much pressure the surface of the liquid is, and therefore the liquid as a whole is feeling by the air molecules pushing down on it. Water vapor, by the way, is a gas. It's just a gaseous form of the liquid. It's invisible. You can't see it. You can't smell it. Steam is not water vapor. Steam is small droplets of liquid water which are suspended. They're so small that they can float, but they are small droplets of liquid water that are floating. They're not a gas. Water vapor is the gas. So what are the factors affecting evaporation? Well, evaporation, you got to remember, is where water molecules or other liquid molecules are leaving the surface of the liquid or of the solid that is wet and going into the atmosphere. At the same time this is happening, water molecules from the atmosphere will be going back into the liquid. It's an equilibrium position. It's not just one direction. It's always happening in two directions. Humidity and saturation is a measurement of how much liquid is already in, how much vapor is already in the atmosphere. If that saturation reaches 100%, that means that there's so much liquid that for every molecule of water that leaves, another molecule goes back in. So there's no overall effect. There's still an exchange between the atmosphere and the liquid, but there's no overall change in the actual amount of liquid in either, or water in either. So humidity saturation is how much water is there. Closely related to that is airflow, because what happens if those liquid particles evaporate and then get blown away is that the saturation goes down. So it's basically a way of controlling the saturation. The intermolecular forces, this isn't just water. Water has a standard set of intermolecular forces. Other liquids, alcohols for example, have different intermolecular forces. A measurement of that is the latent heat of vaporization. The greater the latent heat of vaporization, the greater the forces. So it's not an exact mathematical relationship, but it gives you an idea of the strength of those forces and therefore the amount of energy required, and therefore the rate of evaporation. Greater the latent heat, the slower evaporation will happen. Pressure, again, that's not due to the water molecules which have gone out into the atmosphere, but to the gas particles that make up the atmosphere themselves. If there's a very high pressure, if there's a constant bombardment of those particles, the water molecules will have a harder time of it evaporating. Surface area, for the same volume of water, the greater the surface area, the greater the rate of evaporation, because evaporation only happens at the surface. And finally, and perhaps most obviously, temperature. The greater the temperature of the liquid, the greater the kinetic energy of the particles, and therefore the easier they will find for it to evaporate. So just to give you a visual on what the process is here, gas particles, same chemical, we'll say water, liquid and gas, and the particles of a higher kinetic energy are leaving the surface. Don't forget, as I said, at the same time, some particles will be returning to the surface. Evaporation happens when there's more leaving than are entering. We can actually draw a graph of the number of particles with kinetic energy, and this leads us to one of the consequences and applications. The temperature of the water tells you something about the average kinetic energy of water molecules. We've already seen this. There's a certain amount of energy that's needed to evaporate. So from all these water molecules, those highlighted in green will evaporate. What does that do to the average? It means that the average goes down, which means that the temperature goes down. Now, if the liquid is now cooler than its surroundings, what's going to happen when the temperature goes down? Well, it's going to go up again. How is it going to go up? Because it's going to transfer energy from the surroundings. That means that the equilibrium will increase, and again there will be particles with greater than the required kinetic energy to evaporate. Those will evaporate, average goes down, takes in energy from the surroundings, repeat, repeat, repeat. Okay, this will repeat forever, except that it won't, because the total number of particles will over time go down. So if you spill a beaker of water onto the floor, then that water will over time evaporate. If you leave it in the beaker, it will evaporate, but it will evaporate much more slowly because the surface area is much less. So the water will evaporate and the surroundings will be cooled during that process. So one of the applications, a natural application of this, is perspiration or sweating. You sweat because your body has what's the phrase? Homeostasis. Okay, it loses heat. It wants to maintain a constant temperature, and therefore, by sweating is a mechanism by which the evaporation of water from the surface of your body will lower your overall temperature. Okay, this graph is a bit more complicated graph showing pretty much the same thing. So particles of enough kinetic energy will evaporate. I like this graph because it shows you the difference in the distribution between two different temperatures. Temperature of 300 Kelvin compared to 400 Kelvin. The average kinetic energy is definitely less. It's much more on the 400 Kelvin over here. The same number of particles in both. Okay, so the area under both graphs is the same, but 400 will go to 300. Okay. So that was a brief look at evaporation. Thank you very much.